Hello, this is James Baer with the WebLogic Server Product Management Team. We're going to continue our WebLogic Developer Series today with our second session on distributed caching with Coherence and applying that to the previous session that we did with data access and JPA. We have upcoming sessions still to come on message-driven and web services with Spring, adding RESTful web services with JAX-RS and a JavaScript UI with jQuery, and another session on troubleshooting and performance. As I said, the next session will be next week, and we'll cover Spring, both with JMS and with web services on WebLogic Server. Again, my name is James Baer. I'm on the WebLogic Server Product Management Team. I generally focus on Coherence web integration with WebLogic Server and Exalogic integration with WebLogic Server. In today's agenda, I'll first define Coherence and go over the basic concepts. Secondly, I'll apply those concepts to TopLink grid, specifically adding Coherence support for JPA. Next, we'll apply what we've learned to the Coherence and TopLink grid to the Oracle Parcel service example and look at some code and a demonstration. Finally, I'll cover WebLogic Server and Coherence integration, which was recently improved. Coherence Overview. Coherence has been around for a little bit over 10 years, and it powers some of the most sophisticated financial services, e-commerce sites, logistics, and other high-profile data systems that are very name brand that you would recognize. And Cameron Purdy has been a very vocal member of the Java community and very engaged for a long time. This is how he defines it. A data grid is essentially a system of multiple servers that work together to manage information and related operations such as computations in a distributed environment. So the key words there are bolded that you'll see is data grid. So primarily we're talking about putting data and state into a set of machines, and the distributed, meaning it's not all co-located together on one place, that it's spread over a large amount of computers. At the core of Coherence is its differentiated clustering protocol called TCMP. This is a custom protocol layered on top of UDP, either multicast or unicast. Because we're using UDP, we get the benefit of asynchronous messaging between members. Yet we layer an additional protocol on top, which allows us to have ordering and reliability of the messages. It has other characteristics that are very important. It is peer-to-peer, which is one of the secrets to the way it scales. You can think of other high-profile examples of peer-to-peer approaches used by products like Skype, BitTorrent, and Napster. All of those products have been able to scale extremely well at internet scale. It also has some other characteristics, such as self-healing. It is a mesh architecture, meaning individual nodes can talk to other individual nodes without going to a central lookup service. It has TCP-like features layered on top of UDP, and the messaging throughput scales with the underlying network. There is a Coherence Clustering service which provides a logical view of the cluster at all times to all members of the cluster. It uses a consensus protocol to decide when members are able to join the cluster and when members leave the cluster either voluntarily or through some other kind of unexpected event. In Coherence, you have a Coherence cluster at a logical level at the top, and then services layered underneath the cluster that are available to all members of the cluster. Those services could be examples such as a cache service with individual caches. You can think of caches as analogous to a database table in a relational world, or they could be other services like invocation services, in which case I might want to execute code remotely on another machine. Let's take a look at how data is stored in Coherence. One of the ways with distributed caching that people like to think of it is a large distributed hash map. And at its simplest, that's what's being depicted right here with partition caching. Each of those colors and those boxes that they're in represent an individual node in the cluster. So in this case, when I'm storing several different pieces of data, responsibility for storing that data is actually only with one member of the cluster. The pros of this approach is very high scalability for data capacity and for processing. However, there's a high chance that with any individual node requesting a piece of data that it's going to have to go over the network to retrieve that piece of data. What many people utilize is that same approach for partitions, but also allowing for fault tolerance by storing backups on each node as well. So now each node becomes primarily responsible for some amount of data and also backups for other members of the grid. The backups are guaranteed to be on a separate physical machine as the primary copy when possible, and they're shared amongst the other nodes for all responsibility for all the data. Now let's introduce a new concept of cache clients and contrast that with cache servers. Cache clients are different from cache servers in that they are typically storage disabled. This means they are not primarily responsible for holding data, either the primary copy or the backup copy. They're typically where your application code would lie, and they access the cache servers, which are the JVMs that would, in most cases, be responsible only for holding data and processing. We do have the concept of near caching, however. This utilizes a small, size-limited local cache in the client tier, which allows them to, in some cases, bypass the need to remotely go across the network to access and work against data. We also have concepts for data affinity. This is very important in parent-child relationships. Since we're going to be talking about JPA and object relational mapping later, this concept maps very closely to that. Let's look at some data processing options. Coherence has an event model which allows the cache clients or other members of the grid to listen on individual pieces of data or other events. Let's take a look at an example of a query. In Coherence, a query is executed in parallel across all the members of the grid, speeding up the individual processing time and sending all of their results back to the application where they are collected and then returned to the calling client. You also have the ability to configure what is called a continuous query cache. This is a local view in the client that is always maintained and kept up to date. Let's take a look at how that works. The query is sent to each individual node in the grid that is responsible for storing data and continually runs on those nodes. As there are changes in results to that query over time, they are sent back to the calling application and collected there. Another way of looking at coherence is what we call an invocable map. So instead of always doing the processing on the client or application tier, it is also possible to submit business logic to the grid and have the processing occur local to where the data is stored. In this case, I'm submitting my business logic. It's serialized over the network, sent to each of the individual nodes, and operates there. And it returns the results to the client, but I didn't have to transfer the data in order to have my business logic take effect, just the result. There's another concept in Coherence called triggers. Triggers are pieces of business logic similar to a trigger in a database table that can always operate right before or after data is put into the grid or accessed. Typical uses for triggers are for things like auditing and logging and validation. At its core, we have open source Eclipse Link, which is the JPA reference implementation and also has capabilities for XML, service data objects, enterprise information systems, and database web services. TopLink Grid is a commercial offering from Oracle that builds support into Eclipse Link and layers on data grid capabilities from Coherence on top of Eclipse Link. We have tooling choices for our developers to use either Oracle JDeveloper Eclipse, Oracle Enterprise Pack for Eclipse, or NetBeans. Let's take a look at how Eclipse Link can be scaled in a cluster. With any application, you want to be able to scale beyond one individual node. And with JPA, let's take a look at that. So we have an entity manager, which is an L1 cache, and in each application JVM, you have an entity manager factory, which is a shared L2 cache. We need to be able to keep these caches consistent across multiple instances of our application. If we don't do this, there are some implications. For example, in a write scenario, if I write data and make changes to an entity in one instance of my application, that change will be flushed to the backend database. However, that entity may already be cached in the L2 cache of another instance of my application, and that instance may get stale data. This is undesired. There are two ways to account for this issue. Number one is disabling the shared cache, in which case each transaction will always go to the backend database. The other is cache coordination, in which the members stay in contact with each other so that their L2 caches are consistent. In the disabled model depicted here, we are now missing the L2 cache. There are some implications for missing the L2 cache. Number one is the database is always right, and each transaction will always require all the data from the backend database and construct the entities from the relational model, and there is no internode messaging. The memory footprint of the application increases as each transaction has a copy of each required entity, and the transaction pays an object construction cost for every single access. The database is our bottleneck. Let's take a look at the cache coordination model, in which case the L2 caches are coordinated amongst instances of the application. In this mode, the database is always right, fresh entities are always retrieved from the shared cache, and stale entities are refreshed from the database for access. Whenever we create or modify entities, we have to tell all the other nodes. That involves message latency, and the cost of coordinating all of this communication is higher the larger the size of the cluster, n squared as you see depicted there. Additionally, the shared cache size is limited by the heap in each JVM because each JVM is holding references to all the L2 data for the entire cluster. Scaling JPA with TopLink Grid adds some new capabilities to account for these issues. Updates to the Coherence cache become immediately available to all the cluster nodes, and we allow for advanced configurations to use the data grid to process queries to avoid accessing the database. Here is the depiction of Coherence as our L2 cache. Notice that you'll see that I don't maintain individual copies in each application instance anymore. Rather, Coherence takes responsibility for maintaining the coherent, consistent view of the L2 cache data. There are other models besides caching in the L2 layer. One is called grid read, in which read queries are executed in the Coherence data grid, and writes are performed directly on the database, synchronously, and then Coherence is updated. The most advanced use of TopLink Grid is called grid entity, in which case all read and all write queries from TopLink go directly to the Coherence data grid. Here is a depiction of the grid cache model, which is the L2 that we discussed first. So my application on top, whether that be an enterprise application, ADF, or Spring, uses the JPA APIs, Entity Manager find, let's say. The first step is that Eclipse link will check Coherence to see if it already has a copy of that object in its cache. If there's a cache miss, it will build the object from the database and then put it into Coherence for subsequent access. Coherence can also be leveraged when processing database results. So Eclipse link will construct entities from the JDBC result set, but before building the entire object, we'll just extract the primary key and see if I already have that primary key in my cache. That way I can avoid object construction cost of the object relational mapping. If a SQL query is executed, Coherence can still improve application throughput by eliminating the object construction costs, which can be very heavy. Let's look at what the impact is on writing objects. So my application calls the entity manager.persist or commit. And the first thing I will do is always update the source of truth, which in this case is the database. Upon a successful insert or commit to the database, then the entry is put into the Coherence cache for access in the L2 cache. With JPA, it's very easy to add the grid cache configuration. I can do it with a simple annotation on my entity, or I can do it in XML via Eclipse link-orm.xml. In that case, my Java source code has no knowledge of Coherence or TopLink Grid. Let's take a look at grid read for reading objects. In this case, my application will issue a JPQL query that will come to Eclipse link. Eclipse Link will translate that query into a coherence filter and return the data that's in the coherence cache. The database is not accessed at all. When I write objects using this technique, they are still persisted first to the database, and if that is successful, then the cache entry is updated in coherence afterward, and now my L2 cache in coherence is up to date and shared with all the members of Eclipse Link. Again, we also allow an easy annotation to or Eclipse Link orm.xml to add in this support. There are some limitations in TopLink with 11G R1, and that the JPQL are translated into filters and executed in coherence. They're fairly simple in this release in that they map to a single entity. So I can query employee for all the employee attributes, but if I need to do a more complex query with joins and projections, then those queries will be executed on the database. As with the other ways of configuring different cache settings with TopLink Grid, the grid entity configuration is also available as an annotation with a customizer class, or it could be placed in Eclipse Link-orm.xml to avoid having that information inside your source code. With the grid entity style of reading objects, it's very similar to the grid read style. Queries are performed using the JPA EntityManager.find method or through the JPQL. That will be translated into a coherence filter and result on gets on the coherence caches. The database is not queried by Eclipse Link. If coherence is configured with a cache loader, then a find may result in a SQL call, but the JQPL will not. A cache loader is essentially something in coherence that allows you, when you have a cache miss in coherence, to load data from another backend source like a relational database. For writing objects, it works in a slightly different way. An application commits entities using JPA calls, like EntityManager.persist or commit, and those entries are put by Eclipse Link into a coherence cache. They are not necessarily persisted to the database unless coherence is configured with a cache store. A cache store is similar to a cache loader that we discussed in the previous slide, except in this case it's responsible for persisting changes to a cache to a backend source, like a database in this case. And in this case, you can also decide whether or not to do that synchronously or asynchronously. If you do it asynchronously, it's called write behind. And in that case, coherence will wait a certain amount of time before persisting to the backend data store. For examples where you might be changing a piece of data very often, then coalescing those writes to the backend data source into a single call can be very efficient. How is TopLink Grid different than Hibernate with coherence? The way Hibernate works is slightly different in that it doesn't actually cache the actual objects themselves, it caches data rows. And those data rows are serialized rows in coherence when used with Hibernate. So when you have a cache hit, you still have to pay the object construction cost and the serialization cost to move the data across the wire. And it's paid for every cluster memory for every cache hit. So Hibernate really only uses coherence as a cache, whereas TopLink Grid is unique because it supports execution of queries and avoids object construction costs by storing the objects as objects themselves as opposed to data rows. So in summary, TopLink Grid supports a wide variety of caching strategies, and it's very easy to use Eclipse Link JPA with Oracle Coherence via simple annotations or entries in XML files, which I'll show you shortly. Both TopLink and Coherence are part of WebLogic Application Grid and integrate very well into WebLogic Server. Now let's take a look at the Oracle Parcel service example integrating TopLink Grid and Coherence together. Okay, let's take a look at our Oracle Parcel service. What I've done here is I've just used the domain project that was started last week that Sohail went over. I've imported that into my workspace, and you'll notice that it's a complete project in terms of having a bunch of domain objects managed by JPA. It is using the technique of the orm.xml file instead of Java annotations for the JPA information. One of the first things I wanted to show you is coherence support inside of Oracle Enterprise Pack for Eclipse. So you'll notice by looking at the project properties, I have installed a coherence facet. This is something you can add to utility jars or utility projects, and it specifies that my Oracle Coherence version is 3.6. I can go there and change the version to an older version of Coherence if I wanted. And if we were to look at my user libraries, when you set up that facet, it'll prompt you to create a user library for the coherence.jar. And in my case, the Coherence 3.6.1 jar is available in this location. Once you add the utility, the facet to the utility project, you'll see that it adds a Tangasaw Coherence Override.xml file. This file is how you configure coherence with override information for your cluster. Specifically, you'll set things in this file that relate to cluster connectivity, such as whether to use unicast or multicast. In this example, I have selected several well-known addresses and configured unicast. So in this case, on my local machine, I'm going to have a coherence server listen on port 8088 and 8090. Each coherence process takes up 2 ports, so that's why I have them spaced out by 1. You'll also notice that I have enabled management interfaces. This allows me to use a JMX console to see the state of coherence. The good part about this Oracle Enterprise Pack for Eclipse integration is that I don't have to know all the XML. I can simply go to this design view and put it in the same information, and let's see if I change a property here. If I were to add a well-known address here, 192.168.72.1, and if I were to add 8092, if we were to go back now and look at the source, you see that it's there. Okay, another thing to notice about coherence is another XML file, Coherence-Cache-Config Xml. This file defines the layout of my caches. So in this example, I can use a wildcard, in this case an asterisk, to match any of the cache names, and I'm mapping that to an Eclipse link read-only scheme. The scheme is kind of like a template. Basically, any of the caches that come in that match this pattern will be mapped to this scheme, and then the scheme is defined here. In this case, I'm using a distributed scheme for Eclipse link. This config file is provided by the TopLink grid documentation. And one thing to notice here is this is the name of my persistent unit in my persistence.xml, ops-domain. Let's go compare that. ops-domain in the persistence.xml. Okay, let's run a simple example and make sure my JPA code is working properly. First, I'm going to go to my database and make sure that it has a record in it. It does, okay, that's what I was expecting. I'm going to go ahead and clear that record out. You can see these properties here in my persistence.xml for dropping and recreating the tables. So when I start Eclipse Link, it's going to basically drop all tables and recreate all of them. That way I know I'm starting with a fresh example, so we can do this demo from scratch. So I have a simple class here called query1shipment. It just does an entitymanager.find with the ID of 1. Let's look at the output here. It's connecting to the database, doing all these drops and alters. I do get one exception here about the sequence table already existing, that's okay because we're going to keep using it. And at the very end here, you see shipment is null. That's what I expect. So let's go back to my database. Data sample contents. And there are no records left. Great. So now that I have my database all initialized, I'm going to uncomment that again so that I don't drop and recreate my tables. I want my data to stay there now. And I'm going to go run my simple insert example, which is going to create a new shipment for me. I also have to create some address objects, so I'm just doing a standard constructors kind of POJO approach, right, with Eclipse link, pretty straightforward. And after I create my shipment, I'm just going to call it entity-manager.persist, and that should show up in my database. In this case, I'm not using Coherence at all. I'm just going to go straight from Eclipse link to the database. Run the example. Again, we're getting a lot of verbose information from Eclipse link, so every single SQL statement and SQL connection operation is shown in the log here. So here you can see some of this information. I'm getting the next set of sequences, for example, and I'm inserting records into the shipment parcel table and the shipment table. So if I go back to the database now, go sample my contents, I should see a row in here. Great. I now have a new row, row ID 1. And if I go query against that, I should get a result. So I have a query 1 shipment class here. Let's go take a look at that one. You notice I'm doing a very simple entity-manager.find with the ID of 1. Standard JPA code. Let's go ahead and query that shipment. Here's all my output coming up, connecting to the database. And I'm issuing some select statements directly in the query 1 shipment process. So this is directly in my JVM as a JDBC client, issuing these select statements. This is important to note because you'll see a difference when we wire up Coherence to this. And as you can see, we do have shipment ID 1 with 1 parcel in this external reference. So that worked great. All right, now let's wire in Coherence. So Coherence has this process, this concept of cache servers. Here you see a cache server example. Very simple class. I'm just calling into a Coherence class called default cache server. And the default cache server is our storage enabled node on Coherence. So this is typically the class that's used to store our objects. I'm going to go ahead and start an instance of the cache server. And we'll look at the output. All right, let's analyze what we got. So the very first thing you should notice is this JMX connections. If we go look at my run profile for the start cache server, I've passed along a JVM argument to enable JMX. We'll show you that momentarily, but this allows us to go view the mbeans inside of Coherence. At the very top of the file, it's going to give me information about the configuration that it's using. So here you can see I'm pulling some information from the coherence.jar file, which is the main Coherence library. And I'm also pulling in my override file that we just looked at earlier that defines my cluster properties. So it's good to see that that was picked up. And you can see that the IP and port, in this case 8088 for the port, was picked up and we're using unicast. I know that it's unicast because I see the well-known addresses. If this were a multicast, you would see the multicast address there. So this is using the two values we defined earlier. In this case, I only have one port available right now because this is the only JVM I'm running, but we'll start a second one shortly, and it should bind to port 8090. I get information about the current state of my cluster. So I have one member is this member. The oldest member is also the same one, and I have the list of members shown here. I also see a little bit of information about the death detection that's used. So TCP ring would be a TCP connection to other members in the cluster. And a little bit of detail about the services that are going to be available with this node. In this case, the really important one is the partition cache for Eclipse Link JPA. And you can see that this local storage is enabled. I do have backup set to on so that my data grid has reliability. So let's go ahead and start a second cache server, and we'll compare the output. Okay, great. You can see the same configuration information is, well, actually this is the same process. I take it back, and this is still cache server 1. Let's go look at the bottom. So this is all the same information. This is where we left off right here before, and now I have a couple new entries at the bottom. Member 2 was announced and joined the cluster and joined this service, the Eclipse Link JPA service. And this node is transferring primary partition sets over to the other node to take responsibility for. So as we talked about earlier, Coherence spreads the work amongst all the nodes in the grid. And so since now we have two members, the Coherence cluster is giving an equal share of the responsibility to the second node. Let's go look at node 2 and its system output. In this case, we're loading the same configuration information. And in this case, we are indeed connected to the proper port that I expected, 8090. And member 1 joined my service. These are my well-known addresses, same as before. Now my member set in this printout actually contains 2, because there was already an existing member. And this now shows a TCP connection to the other member. And here's where we made the request to member 1 for an equal share of the work. We can also go to mission control and start a console process. Essentially, I have added in the JRocket mission control plugins into Oracle Enterprise Pack for Eclipse. This requires you to run Oracle Enterprise Pack for Eclipse with JRocket, and you can see that in my eclipse.ini file. Here is the MBean browser, and I have an entry for Coherence, and I get a bunch of MBean information here. So I get the state of the cluster. Here's my cluster MBean, showing that I have 2 members in the cluster, and it will maintain more information over time. I could graph these, run up operations, etc., all off of this view. It's very similar to JConsole, except that it's integrated with a lot of other powerful utilities that come with JRocket Mission Control. And I have a list of my nodes. In this case, I don't have any cache data here yet. So let's go back and start a console process. This is a very simple interactive shell that demonstrates some of the fundamental concepts in Coherence. Typically, you wouldn't use an interactive shell in your production code, but it's very helpful to understand how Coherence works. So let's go to the Coherence console. Now we see I actually have 3 members in my cluster. One thing that is interesting about this client is that I actually use the same exact configuration to start my client with one distinction. I enabled a system property, local storage false, for this client. That means that Coherence should not give this client an equal share of the data responsibility. I am essentially just want to be a client only and not use my local heap in the client to store data. So here's my console process. I am going to pin the console there, and I can type interactive commands like help. And it shows me what the available commands are. So in this case, I can say cache foo, and it's going to create a cache named foo in the cluster using a template that we had defined earlier in my Coherence Cache-Config.xml file. And here's the name of my cache foo, and it's using the same definition we looked at earlier. I can execute the size command and see that there's nothing in my cache currently. I can go back to mission control, and now I have a cache mbean. For each node, I have information about its responsibility of the data for foo. So 0 in node 2 and 0 in node 1. Let's go ahead and put some data into my grid. That happens to be the put command. So I will put key1, value 1. These are just strings. And see it returns null to me. When you put an object in Coherence, it's going to return back the value that was previously in the grid for that key. So in this case, key 1 was previously empty and did not have a value, and therefore it returns null. If I do size, now I have 1, size of 1. If I do get key 1, it should return value 1. There it is. I can go back to my mbeans and see that it's not in member 1. I should expect member 2 to actually have a size of 1 now. Yes, it does. If I were to put a new value, it returns my old value, and I should still have only 1 in my grid, and I do. I'm going to demonstrate one other capability of Coherence for you here, and I'm going to kill the console, and I'm going to kill cache server 2. So both of those processes are gone. Go back to foo, number 1, and now it has size of 1. If we're going to go look at the cache server, you'll see at the bottom, it's restoring from backup. Because this was a backup for the other member, when the other member was killed, it retrieved the value and promoted its backup to a primary copy, and we did not incur any data loss even though we lost nodes in the cluster. So now I'll go ahead and start up my Coherence console again. Run a size. Oh, forgot to do the cache, so cache foo. And has a value size of 1. and a value of 1A just like before. Key 2, value 2. There you go. Great. So now let's add coherence support into JPA and enable TopLink grid. So as we covered in the presentation, there is only one location you need to change. The central location is Eclipse link-orm.xml, the one file I can use to make changes to enable TopLink grid for a level 2 cache throughout the project. So on the shipment domain object, the address domain object, and the parcel domain objects, I have set a customizer for each one set to the grid cache customizer. This will direct Eclipse link level 2 cache interactions to Coherence. Simply save the file and let's try it out. I'm going to start several Coherence cache servers. Cache server 1, cache server 2. Let's check their output. This one is ready. And the second one is ready. Let's execute our query. What I expect to see this first time is that the SQL statements will be issued. So Eclipse link has started. As soon as I issue my find, you'll notice that it goes into Coherence right away because Coherence is configured now to be the L2 cache provider. It joins the cluster now as the third member. In this case, the test query 1 shipment JVM is going to be storage disabled. And here you go. Here you see a bunch of Coherence messages issuing gets. So this query 1 shipment JVM no longer issues select statements directly. It's using Coherence. Now let's go see if we can find out where those select statements came from, because we did get the data back, right? Here's our shipment 1 with our parcels and our external reference. So that is the shipment that's in the database. If we go look at the Coherence cache servers, here's cache server 1. So what happens here is it starts Coherence, and then right after member 3 joins, you'll notice that Eclipse link is loaded, because that's when the level 2 cache interaction came to this node after the find entitymanager.find method was called. So we'll scroll down a little bit through the output. Here you see we connect to the database, and I expect to see a select. There's a select statement, great, right there. So in this case, we're just going to the address table, and that's all that's in this particular JVM. So when we go over to JVM2, I'm going to expect to see a lot more select statements. So similar pattern here, we start Coherence, and as soon as member 3 joins, we start issuing the Eclipse link, initializing Eclipse link, and we connect to the database, and here you go. Here are the remaining select statements used to retrieve the shipment detail. So what you can see from the output up here is this query 1 shipment actually did execute. It sent the L2 cache queries to the cache servers, and you saw that it went to both cache servers depending on the object that was issued. And now if we run the query again, query 1 shipment, this time I'm going to expect to see no SQL statements issued, because we already have the data in our cache. take a look. We're initializing Coherence. All the objects are coming back from Coherence and we're spit out the shipment. Let's go check the cache servers. I'm going to expect no new select statements. So here's where we saw the original disconnect after the first query. And number 4 is another instance of the query 1 shipment coming back. And you notice there's no select statements. Let's go check cache server 2. After member 3 left was the initial instance ending. Member 4 comes and there's no select statements. So there you go. We are able to show that we did not hit the database on the subsequent request. If we were to go look at the JMX console, we'll now see that there are Eclipse link caches for all of our entities, address, parcel, and shipment, and we can see the size of each one in each node. None in this one, none in this one, therefore shipment must be here. And there it is. WebLogic Server and Coherence have recently undergone even tighter integration in the new 11G R1 patch set 3 or WebLogic Server 10.3.4 release. We are now able to use WebLogic Server Node Manager to remotely manage Coherence servers that run on other machines. What this means is that I can, from one central location in the WebLogic Server Administration Console, control my Coherence configuration and Coherence servers in terms of lifecycle and in terms of things like JVM options and configuration. And I can push those out to remote servers and have them started and stopped all from one central location. I have the ability to use the WebLogic Server Admin Console to do this, or WebLogic Scripting Tool, or the JMX interfaces. I want to call your attention to the WebLogic Server YouTube channel at YouTube/Oracle WebLogic. It's something that we just started doing recently, and we're very excited about the potential this has as a way to interact with the community and share information about WebLogic Server. You'll see a wide variety of videos, including things showing off new features that are not yet available, even such as the JEE6 web profile preview. You'll see a couple of videos from myself about using JRocket Mission Control to look inside of your JVM and view WebLogic Server events. We have a bunch of videos about WebLogic Server JMS, and we're happy to put additional videos on there. Just drop a comment to us on the channel and let us know what you'd like to see, and we'll put it in the queue of ideas for us to make a video for.